Welcome everyone to our newest FiberPlanIT webinar. Today we will focus on the planning and design of fiber to the X networks, with X being different possibilities. So we will dive into some specific cases like fiber to the antenna, fiber to the cabinet, and fiber to the node. Of course, FiberPlanIT also supports the planning and design of FTTH, or fiber to the home, networks, but that is treated in previous webinars. And for those interested specifically in those topics, we can always share links to the recordings of those webinars. My name is Raf Meersman. I'm the CEO of Comsoft, and I'm happy to present today together with Jonas Verstuift, our business development engineer for FiberPlanIT. On the agenda for today is a quick introduction on FiberPlanIT and the general planning and design process. And after that, we will dive into the planning of some specific FTTx cases. This will also be combined with an interesting demonstration of how FiberPlanIT can model those examples. And at the end, we will treat some questions that you can leave. So before we start with the real content, just a few quick practical guidelines. So the presentation and demonstration part will take about 45 to 50 minutes. Any questions you have while we are presenting, please leave them in the GoToWebinar question and answers window that you find in this application of GoToWebinar, and we will treat them at the end. When you exit the webinar, there will be a short survey, so we would be very happy if you could leave your feedback there for us. And also, in the follow-up of this webinar in the next couple of days, you will receive an email with a link to the recording of this session, so you can share it also with other colleagues. Now let's first turn to FiberPlanIT and quickly introduce, for those who don't know, what FiberPlanIT is. FiberPlanIT is a unique support software for the planning and design of FTTx networks. The high level of automation and optimization that FiberPlanIT brings allows to make the planning process of FTTx networks smart, fast, and easy. With smart, we refer to the intelligent algorithms that are the core of FiberPlanIT. They allow to optimize the design decisions on how to plan a network in a certain area. Fast refers to the fact that one design calculation on an area of 7,000 to 10,000 homes can be done within minutes. And as such, using that in combination with data preparation, validation, etc., you can easily design an area of, for example, 7,000 homes in less than 3 days, as many of our customers today already report. With easy, we refer also to the fact that we have an easy interface to change some parameters and assumptions that will then be reflected into the design decisions. And the user of the tool can focus on the important aspects of the decision making and not spend his time in, for example, counting homes that pass along a cable and making sure everyone gets sufficient fiber capacity. So overall, our customers have experienced and reported a significant increase in the profit of their FTTx project by introducing FiberPlanIT in the process. And this is, of course, linked to the minimization of costs through optimization, and also to maximizing the revenues by making the right decisions on where to deploy the network or where to start deploying the network. Now, let's have a look at the core functionality of FiberPlanIT. At the start, or at the input of our software, we have two important sets of inputs. The first important input is geographical information, so GIS data. This GIS data is, for example, geolocations of demand points, where demand points can represent, for example, individual homes to be connected, or also antennas or cabinets to be connected to a fiber. A second important geographic input is street center lines. So you see a small example on the slide now. And in fact, with only street information and demand point information, that's already enough to do a greenfield design calculation for a fiber to the home network. But optionally, more information can be added as available or as needed, like, for example, existing ducts, existing poles, central office locations that could be reused, or, for example, also manholes that are available for reusing when deploying fiber. Even some geomarketing information that gives an idea on the potential take rate of different areas, and as such is capable of identifying high potential areas, can be used for specific analysis. A second important set of inputs are the design rules. Within these design rules, the user will define the network architecture. For example, also, the user will define a number of layers within the network and the types of cables and deployment methods to be used in each layer. So also the materials are described, and all the unit costs can be configured, both for material and for the labor to install the whole network. Now with these two inputs fed into FiberPlanIT, FiberPlanIT will do an automatic calculation of an FTTx network for that area according to those rules. And you will receive a geographical output that shows you how FiberPlanIT suggests to create the network in this area. So it shows you where you can potentially place some fiber aggregation points, how cables run from there to the homes where they cross the street, and how the aggregation points can be connected to a central office location. So it's a very transparent output, and you know exactly what the software suggests as a topology and as a network according to your rules. But equally important is that for each calculation that FiberPlanIT makes, FiberPlanIT will also generate a full bill of material and bill of quantity. So you get the whole set of volumes for each set of equipment, and from that cost summary report can be generated that will tell you immediately how much this whole project would cost and what the different parts of the network would represent in that total cost. So a big benefit of FiberPlanIT in this usage is that you can easily change some assumptions on the input, either on the design rules or on the geographical information, and then quickly recalculate the full network and see what is the impact, and as such compare these scenarios within, let's say, even minutes, and make a good decision. FiberPlanIT is also a proven technology. It is available on the market since 2008 in the form of consultancy services by our company, but also since 2011 on the basis of licenses that we sell across the world. So currently we have more than 120 FTTx projects where the software is involved across more than 35 countries, and all of that is more than 50 million homes which have been planned by our customers within these commercial projects. Now let's look at a general end-to-end planning and design process as an example of different steps that can be taken within that process. So the first step that we identify and recognize is what we call strategic planning. In this stage of the planning, we will look at the big decisions, the business case, how much does it cost to deploy fiber in a certain area, but we will also try to compare different scenarios, whether it's, for example, in a PON network, where to put your splitters, which split ratio to use, and each time we are interested to see how does any decision will impact the total cost of the project. And from that analysis, we can make the decisions on where to deploy and how to deploy the network. Once we've made those decisions, we can move to the next step and create an initial design for a first selected area according to the selected set of rules. This initial design step will decide where to put the aggregation points and exactly how to route the cables in the most optimal way for this area. But this still is, let's say, a desktop or a theoretical exercise. So it's very important then to also take that initial design, take it to the field and verify those decisions. From such a field survey, you typically will have some redlining information where you want to indicate which parts of the design would actually need to be changed because the situation in reality in the field is different from what was captured in the initial input data. Now, this fine-tuning step as such will then allow you to shift around some points or clusters or take different decisions, impose those on the design and re-optimize all the rest so you have still an optimized network within the given constraints. This can also be an iterative process, but once the planner is happy with his design, he can finalize that in the detailed design step and transform that into a construction plan, which means at that stage we will also be adding splice plans that give the connectivity on an individual fiber level, labeling on all the objects, and for example also logical schemas. So with such an output, we can hand that over as a to-build plan to a construction company who can then actually build that network. Once it's constructed, it's also important to capture any changes in the as-built and document the network as such in the network inventory system. Within this process, FiberPlanIT will focus on the strategic planning and the initial and fine-tuned design step. But of course, it's very important for the end-to-end process to have a smooth process through all the steps, and that's where our integration with several engineering and inventory tools comes into play, where together with those tools we can support this end-to-end process and bring the value of FiberPlanIT to the planning and design process. Just a few more remarks on some interesting functionalities that FiberPlanIT adds to this end-to-end process. As we said, an important input is GIS data. Now, FiberPlanIT actually also brings a lot of automatic pre-processing of input data. You see on the top of the slide here an example of an area where you have buildings, you have address points, you have pole information, and you have streets lines. Now, automatically, FiberPlanIT can assist to create, for example, aerial drop connections from buildings to existing poles, create aerial connections between poles, or create possible trench locations where an underground network could be constructed. This is all candidates, so afterwards, in the design phase, FiberPlanIT will decide which of these routes to choose depending on the cost. Also, within that design step, as we said, the fine-tuning is very important. Well, the fine-tuning can be done directly on the geographical output, where you can easily pick up, for example, the location of an aggregation point and move it over to a new location, and then recalculate the whole design, and you will get an updated bill of material right away. Also, the interface and the import functionality of a final design into the inventory management tool is very important, as this will save a lot of time. What's important as well is that during this whole design process, we want to give full control over the quality and the output to the planner. And this can mean in some situations that a planner wants to evaluate alternative options than what is suggested by the tool. For example, there can be cases where one rule would actually could be broken occasionally. Let's say, for example, if a fiber concentration point has a real capacity of splicing 48 fibers, but the rule is to keep 4 spare. Well, in some occasions, you may want to break the rule and connect 45 fibers from the start because it could save a lot of money. Well, this can also be done in the fine-tuning phase, and you can immediately see if this once breaking that rule, what it would give in terms of cost savings, and then decide if it's a good idea or not. And also, like we said before, with some field survey information, we can check the feasibility of a certain location and update if needed. And of course then keeping the assurance of quality, because we always see what is the impact of any decision on the cost, and every non-fixed part is always optimized within the constraints of the design rules. And then also across multiple planners, there will be a high level of uniformity, where the rule compliance is always verified and any breaking of rules is reported in warnings. So for the planning and design steps that we discussed earlier, on the strategic planning, answering questions like what is the cost, how to deploy, where to deploy, the FiberPlanIT simulator is the tool that supports this kind of decision making. When we move to the design steps, it's actually the FiberPlanIT Designer, which is another tool based on the same platform that will assist in making these decisions. And as said before, we have specific webinars for the fiber to the home cases on both strategic planning and the design steps. So if you're interested, we can always share those recordings. But today we will now focus on the fiber to the X planning and design challenges, where the X can stand for a lot of things. So we all know that there are a lot of options. There are like more options than we have letters in the alphabet for the X in our FTTx. One set of important variations relates to how far the fiber is deployed in the network. Ultimately, a fiber can go to the home or to the building, but if you have existing infrastructure like a copper twisted pair or coax network, you can actually use parts of that and bring the fiber, for example, also to the front door, to the curb, to the node, or to the cabinet. And then there are also some variations of FTTx where the X represents different market segments like fiber to the office or fiber to the antenna. So within such a context, and looking at the strategic planning stages, it's very important to make the right decisions amongst all these options and decide how to build the network of the future. Of course, we are talking here about deploying fiber, so it's a huge investment because there's a lot of civil works typically involved, even if it's only up to a certain node in the network. And also the networks are deployed for a long time, so a long-term vision is crucial. It means also that we need accurate answers to the most important questions on cost and different scenarios, and we also need them fast because time is short when we are making these long-term decisions. Now there's a common consensus in the market that the ultimate endpoint of the broadband networks of the future is to bring the fiber all the way to the home. But as we said before, in case you have an existing infrastructure, you see more and more that it does make sense also to look at some migration paths to fiber to the home and bring the fiber in the first stage up to a fiber node in the field and reuse those last couple of meters of copper and coax to get into the homes. As we said also before, if you look at fiber to the home and you would only focus on residentials, it's actually you're missing some opportunities because next to those residentials you'll also find some businesses, some antennas that need to be connected, and then if you take them along in your planning stage, you could save a lot of money from making one network for all. And also the number of steps in the migration that you take will be an important question. Do you take really gradual steps and go each time a little bit closer, or do you go, for example, in certain areas with a total overbuild of fiber to the home immediately for whatever reason? So all this decision making is very important, and making the right decisions from the early stages will save a lot of money in the long term. So when we ask the question, what is your strategy for the X in FTTx and which approach on migration would you take? Of course, when we talk to several customers, we see that the cases can be very different. There are a lot of influencing factors that will influence this decision making and the right answer to this question. Obviously, there's the existing infrastructure, and what's important there is what is, for example, also the coverage of this infrastructure today. What is the quality, or for example, also the age of this infrastructure? If it's in certain areas, if the infrastructure is rather old, it could give an increasing amount of operational expenses, and then could be also a trigger to replace it by a new technology. Competition is obviously also very important. If you have an existing infrastructure, but suddenly a new player comes in the market who aggressively deploys fiber to the home directly, it could trigger to move in that direction as well more quickly and pass through some migration paths. Also, the balance between investments and operational costs can be very important. If you move fiber closer to the customer, and so then you're introducing more fiber nodes into the network where you will have to deploy some active equipment. And it means your operational costs can go up because you'll need more maintenance, you'll need more powering, etc. But at some point, for example, a technology like reverse powering, if you're close enough to the customer, could bring a solution that at that point the powering, for example, could come from a customer side. So there's a lot of questions to be answered there as well. Also, what is the market demand for broadband today? Are people willing to pay more for a certain speed? And for example, what's the status of the deployment of small mobile cells? And do we need a fiber backhaul for those? So you can think of different approaches. For example, go with a fiber to the node plus antenna plus offices, and then migrate after that to the home. Or, for example, go with fiber to the cabinet and to the antenna with a next step to go to fiber to the home. What's important in those scenarios is that you also take along the capacity that will be needed in the end when you start deploying in phase 1. So now I'll introduce you to 3 specific examples that we will then also treat in a demonstration of the software. The first example is the example of a DSL operator who has an existing copper network where he has these cabinets and VDSL2 deployed from these cabinets. So a fiber currently will be coming to these cabinets. There we have a conversion into the electrical signals on copper. As an example, again, case by case can be very different, but let's assume as an example in this case, the typical copper lengths from the street cabinets that remain are between 10 and 1,000 meters and can be in rural areas 2,000 or maybe even more. Now, a typical offered speed with this technology, and considering distances up to 800 or 1,000 meters, will be around 30 megabits per second. Now, the objective is to see if we reduce the copper length, if we can increase the speed that we can offer. And you see an interesting figure here on the different options that are available. A picture by Alcatel-Lucent, by the way, where you can see, if you look at the VDSL vectoring, what we said about 700, 800 meters. Okay, introducing vectoring on that without bringing extra fiber could already increase the bandwidth that we can offer. But if we, for example, also shorten the copper loop length to 400 meters, we could deploy V+, which could increase the bandwidth to 200 megabits. Or we could use G.Fast, but then we'll have to limit the distance of the copper to 100 meters, going up on bandwidth to 500 megabits in order of magnitude. Or we could go even up to a gigabit if we bring it really up to the front door and having only a couple of tens of meters of copper remaining to enter the home. So you see in this case, the distance that remains on the copper network will heavily influence the bandwidth that we can offer. So we will now, in the demonstration, evaluate a couple of scenarios. The first scenario will be a scenario where we reduce the copper length to 400 meters and deploy fiber to the cabinet, be it a new cabinet with VDSL 2+. Or a second scenario where we deploy the fiber to the curb or to the drop point with G.Fast and a maximum copper length remaining of 100 meters. And we will also consider in these scenarios an extra parameter where we can play with, which will be the minimum number of homes per fiber node. Because if we, for example, only have 2 or 3 customers in a rural case that will end up on the 100-meter distance, it could be economically not viable to deploy this technology in that part of the network. So we can impose a minimum that we need to get in that range to deploy such a new fiber node. The second example we will treat is the example of an HFC operator with an existing coax network and deploying DOCSIS 3.0 on that. Here, as with the copper network, it's a matter of looking at how many homes are currently connected to the fiber node that is already deployed. Let's assume we are in the range of 500 homes per fiber node. And it could be in this case that there's typically still 2 or 3 amplifiers on the coax line to amplify the signals for those homes. On such a network, you could probably offer speeds of like 300 megabits per second download speeds. But the problem is here that the coax is a shared medium between these 500 users. So when in peak time, multiple users are using the capacity, there's no real guarantee on the speeds that you can get on this network. So again, the idea is to increase the speed by lowering the amount of customers that are on the shared coax sections. So some options that we can evaluate, for example, is to reduce the number of homes per fiber node to 64 or to 32, or go all the way with fiber to the home. And then the last example is a mobile operator who deploys his 4G cells, which will also increase the data volume and, of course, be smaller in range, so he will need more antennas. The objective then is to look at the fiber backhaul to ensure the maximal mobile data user experience so that there's no blocking in the backhaul and that people can use their mobile volumes to the maximum extent. There are some options which could be considered in this case. For example, you could consider reusing existing ducts from another operator who would then be represent the rental cost. Or you could deploy your own infrastructure and ducts and cables in a greenfield situation. And another scenario would be to answer the question if we introduce also redundancy in the backhaul, so that there's a backup path in case of a failure, what would the extra cost be to do that? So I'm happy to hand over now to Jonas to give some demonstration on these 3 examples.
Thank you, Raf. Like Raf explained, I will demonstrate 3 different scenarios that show the flexibility of using FiberPlanIT in 4 FTTx scenarios in FTTx projects. And we will look at 2 migration scenarios where we push fiber deeper into the existing network, and 1 greenfield FTTA fiber to the antenna scenario. Let's start with the first scenario. So in this first scenario, I've selected an area of around 4,000 homes in a quite a rural area, but we have two center locations which are a bit denser. The first scenario handles a copper scenario, so fiber to the drop point or fiber to the cabinet scenario, and the input data that we load into the software for handling these type of scenarios are the street center lines, which we can use as a basis for doing new trenching locations. And we also load in the existing cabinet locations, which are being fed by fiber at the beginning of the scenario of the project already, and we load in the existing copper infrastructure, so the copper cables connecting the demand points, so our building locations with the existing cabinet locations. like I said, the streets can be used as the basis for new trenching deployment, and there our automatic pre-processing steps come in very handy. So what this will do, and I just switch on the layer, so I did this before the demo. What this will do, as Raf already explained in the presentation as well, will generate possible trenching locations next to the street where new trenching can be done and where new fiber cables can be deployed. So we also give full flexibility to the user to remove any trenching locations, or for example, to have smaller streets, so to have better input data there. The type of scenario that we will look at is a scenario where we bring fiber up to 400 meters from our demand points to be able to offer higher speeds, and also a scenario where we place fiber up until the drop point, so within 100 meter of our demand points. So for this, we can edit configure three different parameters. So one is the distance. So for being able to support a certain type of technology, we need to be within a certain distance of the demand point, and we will reuse the copper infrastructure to get from the new node that we will place to our demand point. The second parameter that we can configure is the maximum amount of buildings, of homes that we want to place on these new nodes. For example, if we limit this to 16, then we can place our active equipment in a closure. If this is more 192, for example, then we need to place already a cabinet, and there will be a cost difference between the two types of equipment, of course. A third type of parameter is the minimum amount of homes that we want to place on these new nodes. As you can see here, we have some quite rural parts in this area here, and it won't be economically viable to place a new closure or a new cabinet for maybe only 3 or 4 homes. So the different colors that you see here are the current copper routes being connected to our existing cabinet locations. And what the software will do is it will reuse those routes to keep serving the homes, but will place new nodes. So let me switch now to the output view for this area. So I did a calculation already beforehand. And what you see is this is now a scenario where we want to bring fiber within 400 meters of our of our demand points, and for this we will need to place new cabinet locations and bring fiber to these new cabinet locations. So what you see here, the blue cable is our feeder cable, using new trenching by the side of the road, feeding the new cabinet location that is placed here. And from this cabinet location, we serve the different buildings via the existing copper routes. So the software will not place any new copper routes. So any new copper cables will be laid out. The software will place the new nodes and will calculate the fiber routes for getting to these new nodes. If we have a look at this rural part here, what you see is that we set a minimum amount of homes for placing a new node. So the red buildings fall outside of the 400 meter cap that we configured, but because we configured that the minimum amount of homes should be around 34. There's no way possible here to place a new cabinet where we get to this minimum amount of homes within the 400 meter range. So the software will take this into account, and by lowering the minimum amount of homes to be within the the distance cap, we will increase the coverage, of course, but we will also increase the costs that come with that coverage. I also calculated a different scenario for this particular area, where we want to bring fiber within 100 meter and being able to support the G.Fast scenarios. The maximum amount of homes that I configured to be placed on a new node is 16. So this will allow us to, during construction, allow you to place place the active equipment in closures and save costs there. And the minimum amount of homes is 11. So what we see here, if we zoom into this particular area, you see that these 3 buildings will fall outside of the distance of 100 meter for this new node here. And this is because there's no way possible to get 11 homes on a new node and 11 homes within a 100 meter range. To give you an idea, this particular route up until this point is already 130 meter. So the software takes this into account, and some buildings will fall outside of the range and you will not be able to offer the higher speeds that come with the new technology. We can zoom in to the effect this playing around with these parameters has on the costs, the amount of cabinets that should be placed, or the trenching that is needed. And I did a couple of different scenarios where for G.Fast, where we increase the minimum amount of homes that should be placed on a new node. And what you see is that if you increase that amount, the minimum amount of homes, of course, the coverage and that you will be able to reach will lower as well. Definitely in very rural areas where the distance between the homes is very far, then increasing this number will mean a lower covered percentage. Of course, together with lowering the coverage, the total cost will also lower, and the amount of cabinets and trenching will also go down significantly. Now, if we have a look at the difference in coverage, looking at a minimum of 8 or 10, so this is a coverage difference of 20%. We go from around 60 to around 80% coverage percentage. But if we look at the amount of extra cabinets that are needed and the amount of extra trenching, we see here in this particular case, so this is very case specific, we see that we need an extra 60% of cabinets for getting to this 77% coverage percentage, and the total cost also goes up with 50 together with the trenching difference. So it's very important to go to have a look case by case at the different scenarios, for check what the minimum amount of homes is that you want to place on these new cabinets, to not go over budget and spend too much money during your deployment stage. So this is a bit about the FTTx scenario for copper infrastructure. I also have prepared a demonstration for looking at an HFC scenario, so where we read in the existing coax infrastructure. So the same principles apply a bit for FiberPlanIT when looking at a copper or a coax scenario. So the type of input data that we need for doing this type of scenario are quite similar. We also need our street center line data and demand point data. And we can read in the current coax routes and cables, together with the tab boxes, amplifiers, and existing nodes that have a fiber connection at the moment. When looking at coax, instead of lowering the distance, what we will do here is lower the amount of homes that are connected to our new nodes. And we will look at two different scenarios, one for 32 homes and one for 64 homes. And I added another parameter in this particular example because it can be quite interesting to look at antenna locations that need point-to-point fiber connection when deploying new fiber for an FTTN scenario or an FTTH scenario. So in this scenario, we have our antenna locations and our homes that we want to serve with fiber to the node. So reusing the existing coax infrastructure and placing new nodes. So let's have a look at the output data. 1 minute. Okay. So looking at the output data, this is now for placing a new node for 64 homes and having a point-to-point connection to our antenna locations. And what we see is that our existing coax routes are being reused, so the blue lines are being reused for serving the buildings, and we have some new nodes being placed for serving that are being served with fiber to guarantee the speeds for the buildings. So this is quite similar compared to the copper scenario. Together with this outside plan design, FiberPlanIT will always generate a cost breakdown, so a detailed bill of material. So let me open this now. In the overview, you will see exactly the type of equipment and the volume that is needed for each type of equipment for realizing your design. This is based also on the unit costs that are needed as input data for the software. And if we look at the other type of scenarios, so you have for the design that you saw was for 64 buildings on a new node and the antenna locations. We can also just look at the 64 home clusters. Of course, if we compare the costs between these two scenarios, we have 485,000 for 64 home clusters. The cost will go up when also considering the antennas, but you can spread it out over more units, so it might be more interesting to take into account also the antennas when doing the new deployments. Definitely, if you want to do this also in a later stage already, then it's very good to look at this from the start and take it into account. Looking at the 32 home clusters, so the total cost increases more because more new nodes will be needed, and more trenching will be needed for the fiber routes. And looking at FTTH scenario, the costs will increase even more in the end. Now, the third scenario that I want to show you is greenfield fiber to the antenna scenario. So here we see a city, the city of Ghent, and the blue dots represent all the antenna locations that we want to connect with fiber. Here we can see some existing ducts, some existing conduit infrastructure that can be reused. So FiberPlanIT will use all the cost information, so unit cost information, for doing new trenching deployment and reusing equipment where possible to lower the costs in the end. So if we have a look at the result here, what you see is these brownish lines represent the new trenching possibilities. We see that not all of these new possibilities are being used. The green lines are fiber cables together with the blue lines, and we see that only a few of these are being used. Now, if we zoom into the part of the area where we had our existing ducts, we see that the software chooses to reuse this existing duct for routing the fiber cables and then branching off right after to serve this particular antenna right here. Now, if we have a look at a scenario where this existing ducts could not be used, then the software will need to reroute the cables to find a more economic route, because the existing ducts in general have a lower cost of reusing it compared to trenching. Now we see before the cable was running at this side here, and now we see that without having the possibility to reuse this existing infrastructure here, then the cables are being rerouted to a more economic way, taking into account that only new trenching is available. So the software is able to handle that type of information and always tries to minimize the cost information. So this was it for the demo part. So let me hand back the word to Raf.
Thank you, Jonas. So that gave us a good idea about the possibilities of using FiberPlanIT to handle these different scenarios for FTTx planning. And just to summarize how a result of comparing different scenarios could look like, this is an example of some of these outputs plotted on a graph where you can get some interesting insights. For example, well, if you look at the V plus 400 meter scenario, like we saw in the simulations by Jonas, we can increase the coverage if we lower the constraint on how many homes on a new fiber node, but it will increase our cost significantly to get really to those last percentages in this specific case. On a 100 meter scenario, you see an even bigger increase in cost to get to only 50% coverage, and to reach 80%, for example, we are at like 10 times the investment as for the 400 meters. And then interestingly enough, if you plot also the figures for a fiber to the home network, and for example, with an ideal 60% coverage selection, you see that you can actually choose with a similar investment in this case to reach 60% with fiber to the home, or to reach about 75% of the homes with a G.Fast solution. So obviously these results are very case specific. Here we have an area which was relatively sparse, and results can be very different, but it shows you that with such simulations and such results you can really make this kind of decisions in a well-informed way. So to conclude some of the things we've seen, so we've seen some examples of different FTTx projects or designs and questions where we could get an accurate cost for that project for a certain area within minutes. This both for fiber to the node or to the cabinet or to the street side or to the antenna. Including also automatic identification of fiber node locations. I think that's also very important to notice, that it's also analyzing where to put those new fiber nodes on the existing network. We've also illustrated how easy it is to evaluate the different scenarios. So moving the fiber closer to the customer with all the options available can be calculated and compared. And you can also look at migration paths and different options there. Also important to mention is that the existing network is obviously an important input in the FTTx scenarios, and they need to come as input to the tool, normally from the inventory system. Now, in case you would not have that data available or the data quality would be insufficient. Note that for strategic planning purposes, the existing network could also be auto-generated, which will not be exact, but it will be realistic. And then the calculations that one makes in terms of the scenarios and comparing the costs of different scenarios could still give a very good indication of the different costs across those scenarios. So overall, I think these examples clearly show that through making these analyses and making these decisions, that we can really assist in turning the planning process into a profitable business. And it's not only us who are saying this, also a lot of our customers are testifying about the benefits that FiberPlanIT brought to their FTTx project and the increased accuracy for generating numbers that they could use in their either strategic planning or design phase. So the final remarks then, we've seen here some examples of the strategic planning with FiberPlanIT. Note that although it's available as a software, we are also engaged with a lot of customers in a consultancy mode when it comes to this kind of thing. So there is expertise available on that as well. When it comes to supporting the real network design with the FiberPlanIT designer, this is really more on a software level. And there it's also important to note that functionalities like moving the calculated fiber node to a new location based on field survey, for example, or changing the customer clusters behind it can also be done. So you can also interact with this type of design mode and then have a new fiber to the X scenario based on those changes. And if you're specifically interested in that designer part, we can always set up a specific demo for that. So that's it for us for this general part. And I think we can still spend some 5 minutes on some of the questions. Please also feel free to add more questions at this time. We'll have a look at it. And if we don't find the time to treat your questions in this session, we can always also come back to that on a one-on-one case. So one question I have here is, where do you get the GIS input data? And okay, maybe directly related is another question. What if the input data on the existing infrastructure is not good quality? So Jonas, can you comment on that?
So most of our input data comes from the customers. Either they have it themselves or they contacted some specific services or government for getting the data. In most countries, you can also get street centerline data from OpenStreetMap. For getting the demand data there, the demand point data, so the building information and detailed information there, you can ask the government, or there may be some specific services in your country that can gather this information. Related to the existing infrastructure, if it's not of good quality, then either it's poles or existing duct information, you can already start your design with the information that you have. Before going out and deploying your network, you will definitely need a field survey, and then you can gather the information in a more detailed level. And FiberPlanIT is very flexible in fine-tuning your design. So even right before deploying your network, you can still do some fine-tuning, or you can do the field survey at the start to gather the correct amount of information at a high detail.
Okay, thank you. Another question here is ComSoft a GIS environment, or does it also work with other GIS tools like Esri, etc.? Maybe related to that as well as, is the GIS data, does it need to be in a specific format?
Yeah, FiberPlanet, in the standalone version, we use QGIS for manipulating the data. We work on shapefile data, but any type of data in any type of GIS format, if it's GIS data, can be converted into this sort of data for using it. And next to that, we have a lot of different integrations with inventory systems. There's definitely a possibility to integrate with new systems as well. So there we are also quite flexible.
Okay, thank you. There's a question here on, do you support ring networks?
Yes, this is supported. So we have a couple of customers that use this type of networks as well. So both on distribution level or feeder level, we can use a ring infrastructure. So that's definitely something that's supported.
Okay, and then okay, maybe a last question to conclude. What's the typical size of one area for calculation, and what is the calculation time for that?
So normally our customers use the software for calculating one CO area, central office area, at a time, and divide up their complete region into these different areas. The size of these areas can depend a lot. I think most of the time around 5 or 10,000 homes. And the calculation time can also vary between a couple of minutes up until an hour, I think.
Okay, and maybe also adding to that is that those calculation times are really on the local workstation even, so not on specific hardware or special hardware that's not needed. Okay, I think we can wrap up for today. I would like to thank you all for attending our webinar today. And as said, we would very much like if you could leave your ideas and feedback and suggestions in the survey, and look for the email in the coming days with the recording so that you can also review and share whatever we showed today. So thank you all for now, and hope to see you soon again. Bye-bye.